trees.
Yes, thank you very much, Marcus, and thanks for the invitation to speak here.
Great microphone.
Okay, so this is a talk about an application of polynomial optimization in biology. Let's see if that works. Okay, so what is a phylogeny? Sorry that this doesn't show up very well, but a phylogeny is a kind of a graph, a tree, in fact, in most cases, unless you're a bacterium, that shows the relationship between different extant species or taxa. If you're closer on this tree, so a laser pointer on here. Then you're more closely related in some sense. And so there are two versions of this. One is the unrooted phylogeny. So we have, in this case, 5 extant species. They're related somehow, and there is some kind of common ancestor somewhere along this tree, but we don't make any specific assumption as to what edge this ancestor lies on. And so in this kind of unrooted viewpoint, there's no direction of evolution. You could evolve from an orangutan to a human, or from a human to an orangutan. Because they can somehow they exchange genetic material, I guess, in asexual fashion.
Okay.
So even if there's speciation, they can still exchange genetic material, and then it's thought that this is not an adequate model for bacteria. There's also the rooted viewpoint, where we explicitly assume that there's an ancestor somewhere on a specific edge, and then there's evolution in a particular direction of time, and this seems to be the topology of the phylogeny of these 5 species that biologists believe is correct. But there are a number of questions that biologists would like to answer in this context. What we have is, what we can observe is the extant species. So we have a lot of information about these. We can sequence their genomes, then we can align the genomes. We can find genes, for example, that have the same function. And then we can compare them, and we see that they're very similar in many places, and there's some small differences. So biologists have sort of methods for aligning sequences, and then they identify what's called a site, where they can compare these sequences. And on the basis of that information, they would like to answer the following questions. What is the correct topology of the phylogeny? So who's related more closely to whom? And how long are these edges in terms of physical time, or maybe mutation event time? And how long ago did the common ancestor live? And can you reconstruct the genome of the common ancestor? And of course, these are not questions that are mathematically well posed, but you can set up models under which they become mathematical problems, and there are many different models. So here is, for example, a situation where you may think of a site not necessarily as a specific nucleotide, but some trait, like the diet of extant species, and you'd like to know what is the diet of the ancestor. So reconstruction models, or should we say methods, because some of the reconstruction methods are not based on a model. It's just someone invented an algorithm and says, look, we're using this and we get this phylogeny, and that seems right. So there are lots of heuristics that are based on kind of distance. The idea is obviously underlying all of these methods is that if two taxa have very similar genomes, they should be more closely related than two taxa that have very different genomes. But how do you measure that distance and so on? So there are distance-based methods and there are character-based methods, and I will tell you in the next slide what a character is. And here there are essentially two families of, or two approaches. The maximum parsimony method that leads to a very simple mathematical problem that can be solved in linear time via dynamic programming. So you get very quickly, you get answers. But it's not based on any kind of stochastic model of evolution. So you don't have, you can't bring in any kind of information about the dynamics of substitution. And then you've got the models that do take into account models of substitution, and then you'd like to know what is the most likely tree, maximum likelihood estimation. And that's where polynomial optimization comes in, because these problems naturally lead to polynomial optimization problems that have a lot of special structure that I think can provide an interesting class of examples. So a character on a tree is simply a map from the set of its leaves to a set of finitely many possible states. If you could think of maybe if you think of nucleotides, this might be 4 different states in the case of the diet that I showed you before. The diet example, there were 2 states, frugivore or folivore. And then you'd like to extend this character to the internal nodes of the tree, and any such extension, well, it's called a character extension. So chi bar is an extension of chi if when you restrict it to the leaves, you get back chi. And then you can count the number of changes that you observe for such a character extension. So you look at all edges u, v, where u and v are nodes in this graph. And you count the number of edges where you have 2 different characters on adjacent nodes. And that's a changing set. And the cardinality of changing set is what you're most interested in, denoted like so. And as we will see, the maximum parsimony method simply tries to minimize the number of changes. So minimize this little ch of chi. So what is the input? The input consists of aligned sequences of different taxa. And here I've got 3 aligned sequences, and I use 3 different alphabets for each site. And that's because a site can be more than just a nucleotide. It could be a whole gene, or it could be a few group, a little group of nucleotides and so on. But I assumed in this example that there are 2 versions of each. So I've got taxa 1 has the first version at the first site, and taxa 2 is the second version, and so on. And so each column generates a character as in what was introduced in the previous slide. So a pattern of assignments of these characters to the leaves, our extant species.
Sorry.
Yeah.
Extant?
Extant means existing. Yeah.
Existing. So you don't look at extinct taxa.
No. The extinct taxa are what we are interested in. So we know all about the extant species, but we'd like to infer how the extinct.
In the phylogenetic tree, there are some leaves which are not, which could be extinct taxa, right? Or not? or are the leaves? By
Oh,
definition-
right, yeah, but you don't have any information about that part of the tree, so you can't infer anything about it, right?
So they're
unless
simply
you
not-
extract
they're
DNA
simply
from
not
the bones.
in the tree unless they are internal nodes.
Yes, so, I mean, you basically that's, of course, there's some branches that have disappeared. You can't see and you can't infer anything about them. But now you see that if I assume that there are only two characters, the character set, the cardinality of the character set, I call that R. The cardinality of the number of sites is M, and the number of species is N. So now in most substitution models that biologists use, they use they assume, for the purposes of dimensionality reduction, that the substitution probabilities are symmetric. So the rate at which an x turns into a y is the same as the rate at which a y turns into an x. Okay, and therefore, although the rates for the different sites may be different because these are different different types of sites, I can arbitrarily call the character of taxa 3 in the entire last row an x, right, and just flip around the other characters. So that means that I can actually characterize these characters by looking at only taxa 1 through n minus 1, and that's called a split pattern. So in this first column, we have the split pattern x, y, because I can throw away the information that the last column contains an x. I know that, right? And that gives a convenient way of identifying the split pattern by the subset of taxa 1 through n minus 1 that have the opposite character or character different from taxa 3 in the case of r equal to 2. So now we observe different split patterns or characters at different sites, and I call the split pattern observed at site I, alpha I, or if you want to think in terms of characters, I call that chi I. And then I can count the number of times I observe the same split pattern. And if I put all of these cardinalities into a vector, which is of size r to the n minus 1, then this is called the observed sequence spectrum. So maximum parsimony simply tries to find a character extension that minimizes the number of changes across internal edges. So it minimizes this function little ch of chi I bar across the different sites. So I can do this for each site separately and then just add up. And then it's very easy to give a dynamic programming algorithm that runs in linear time. So that's an efficient problem to solve if the topology of the tree is fixed. Of course, if the topology of the tree is not fixed, you have to kind of iterate over all possible topologies, of which there are exponentially many. There's a theorem that shows actually you can't do anything better than iterating over all these exponentially many topologies. There's an NP-hard problem. So here's an example. For example, 2 sites, 2 characters. So this is what I observe in the extant species, and the most parsimonious set of mutations is given by assuming that the ancestor of these 2 had the character XX and the ancestor had XX.
The leaves are symmetric. I mean, you have X, Y, Y, not symmetric because you don't have Y, Y.
Oh, I just didn't want to give you a large example because you can do it with YY as well. So note that I mean there are 2 mutations required, or one each on these at least one on each of these edges, no matter how you assume the state of this ancestor to be. But then to minimize the overall number of mutations, there has to be an XX. So this, right, so this is a very simplistic method, and it doesn't give you any information about time. You know, when, how long were these edges, how long ago did a common ancestor exist, and so on. It just gives you some idea of reconstructing the state of an ancestor, and it often gives misleading results or non-intuitive, biologically non-intuitive results. So a much more sophisticated method is based on giving a stochastic substitution model and then running a maximum likelihood approach. Again, we have the small maximum likelihood problem in which you fix the tree topology and you'd like to infer what are the substitution probabilities, or equivalently, if you know about the rates of substitutions, what are the lengths in terms of time of each of these edges. That's a small ML problem. And then there's a big ML problem, which is also assuming that you don't know the tree topology and you have to optimize with the tree topology as well. Now, of course, the big ML problem is harder than the small ML problem, but the small ML problem is already interesting because often you have many different ways of establishing, say, the tree topology, and you'd like to have confirmation about the length. So the typical substitution models that are, or substitution model that is considered is the symmetric Neyman NR model, which is simply a continuous time Markov process that evolves over this tree with symmetric and identical substitution rates for a fixed site. You assume that mutating from state I to state J happens at a rate lambda, which is fixed for all ij. And so that means that at a rate you lose state, if you're in state I, you lose probability mass, if you will, with at the rate minus r minus 1 lambda. So it's a Poisson process that runs at this rate. And then if you know what the length of the edge is in terms of physical time, then the matrix of transition probabilities over this edge from between all states is given by this matrix exponential, and you see that actually it's a matrix that, because of the special form of Q, it has constant entries down the diagonals and constant entries in the off diagonals, and there is one-to-one correspondence between these parameters PE, this probability PE, which I will later use as a decision variable in the polynomial optimization problem, and physical time. So, for example, if you consider the N2 model, this relationship is given by this first line up there. So it's very simple. And the expected number of substitutions per site along an edge is simply lambda times the time. Now, there are two approaches to ML that I would like to discuss. The first one is the standard approach that is being used in the literature. And so what they do is they take these lengths of edges, as in number of expected number of substitutions, and expand that into a vector which they call Q alpha, which has an entry for each split pattern. And the split pattern will take, Q alpha will take the value lambda TE if there's an edge that induces the split pattern. And what I mean by inducing a split pattern is, for example, here I've got a split pattern XX or YYXX, and there's an edge E in between, which when I cut this out, I say these guys are all in the connected component. They have the same character, and these guys are all in the same in another connected component. They have the same split pattern. Then E induces the split pattern. Of course, there are only very few split patterns that are induced by edges. So this vector has a lot of zeros. Okay, so if split pattern is not induced by any edge, then you give the value 0 to this vector, and then there's also the split pattern, the empty split pattern. You give it this this number here, and then there's a theorem by Hendy and Penny, which is later generalized, that shows that you can now, given the vector q, you can easily deduce the vector that gives you the likelihood or the probability for each split pattern to occur for each split. So given an alpha, I can ask what is the probability that the split pattern alpha occurs given these probabilities of substitutions across different sites. Call it S alpha. I have one of these probabilities for each split pattern, and then the vector q is related to the vector S via the Hadamard conjugation, and that's a convenient way of computing all these S's. And so that leads to the first approach, which is to say, given the split patterns that we observe across the different sites, how should we choose S so as to maximize this likelihood, which is assumed to be just independent probabilities. The sites are independent, so you multiply these probabilities together. And so essentially the decision variables are these probabilities S for the split patterns. Of course, what we're after is Q, but there is a correspondence between the S's and the Q's via the Hadamard transform. And you've got equality constraints in that all these Q alphas that correspond to split patterns alpha that are not induced by an edge must be equal to 0. So Q alpha of S is equal to 0. That turns into a polynomial constraint by setting up the equation in the Hadamard transform and then taking exponentials, and you get a rational expression must be equal to 1, and then you multiply through by the denominator. So you get polynomial equations which have very special structure. And then you've got further constraints, which you call molecular clock constraints, in that you know that certain times are equally long, and therefore the substitution rates must have been the same, and that allows you to derive that some of these S's must be the same. So you essentially get equality constraints that allow you to eliminate some of the variables. And so Chor and Sneer used this approach to essentially solve the resulting polynomial optimization problem in the case of four taxa and two states. They solved this via algebraic techniques, essentially via elimination. So they set up the KKT system, which is a system of polynomial equations, and they solved it algebraically. But of course, this is becomes very quickly very complicated. In fact, they did this for this fork topology, and you do it for the comb. It becomes more complicated because you can eliminate fewer variables. The reason you can eliminate variables is because you've got this kind of structure at the bottom. So the more fork-like topology looks like, the more variables you can eliminate, and therefore you get a simpler system. So the second approach is to use these variables P that I introduced. And it involves kind of a trade-off in complexity. So whereas the first approach solved a pop in R to the n minus 1 variables and was essentially an unrooted approach, the second approach solves exponentially many variables in linearly many, exponentially many pops in linearly many variables. So if first approach has exponentially many variables for only one pop. In the second approach, you have exponentially many pops with just linearly many variables. And here, the idea is, well, why do we get exponentially many pops? We condition on the root state of the state of the ancestor. And of course, there are exponentially many of these. But once we condition on that root state, we can use the linearly many variables PE, one for each edge, and there are 2n minus 2 edges. We can set up the likelihood function, which you can easily evaluate by recursion using the Tower law. And then we get inequality constraints from upper and lower bounds on the probabilities. You may have other bounds. So this bound just arises from the fact that we have a continuous time Markov process that is ergodic. So PE can never be larger than the probability that these states take under the limiting distribution. But there may be other bound constraints that arise from limits on the time, on the length of each edge that you have obtained from other methods. And then we've got equality constraints, which arise from the molecular clock. So here we know that if I have, for example, this tree, and I move down from the ancestor via this edge 2 and then down edge 3, then if I multiply the matrix of probability, transition probabilities P2 with P3, then that must be equal to P1. And so I get polynomial equalities in each entry. I can extract these, and in fact, there is a variable change that efficiently sets up all of these. So you get one of these equalities for each path from the ancestor down to a leaf. And so we end up with this pop up there, collecting all the inequalities in equations. Due to the nature of the inequality constraints, we know that Poutinar's condition applies, and that means that we can, if we use a sufficiently high degree extension, we will eventually be able to solve this problem exactly. And then we follow Jean Bernard's approach by setting up these localization matrices M omega, and turn it into semi-definite programming problems. Again, the fork topology is much easier to solve than the comb topology, because in the comb topology, the degrees of your polynomials will be much higher, because the depth of the tree is deeper, and then also every time you have two states that are different in the leaves, then this probability on the next edge up will actually not appear in the objective function, so thereby reducing the degree by 1. So there's additional reduction of the degree that occurs. Then one of Marcus's theorems allows us to actually extract the optimal points P star once we know the optimal Y star. So this is not the convergence as in omega really has to go to infinity, but for sufficiently high omega, you get that Y star is a Dirac measure up to numerical precision in the case where our pop has a unique solution. And if it doesn't have a unique solution, then we can introduce small random perturbations, linear perturbations to our objective function, and we get all the solutions. And it worked very well. In the case of 5 taxa, the 6 taxa is a bit more challenging. But in conclusion, I can say that this approach achieves unparalleled accuracy over heuristics, because the heuristics that people use in this field are what they call hill climbing, which is kind of a steepest descent method, or steepest ascent, if you will. And on that basis of their heuristics, they had a conjecture that said that the maximum parsing method and the ML method will always yield the same ancestral state on the NR2 model, and with polynomial optimization, you can easily show that that's not the case. I should say that one of the great advantages of this approach is that you get upper and lower bounds on this likelihood, and that means that when you try to solve the the big ML problem, you don't have to solve your POPs to high precision to be able to discard some topologies, because their upper bound is below the lower bound on, say, another topology. So you can use kind of pruning by bound, and so that gives you an interesting approach in this case. Thanks.
There's time for short questions.
One thing I didn't understand, so if the sample size is large, the likelihood function will be a polynomial of very high.
Right.
So how do you deal with that?
Right, yeah, okay, yeah. I jumped over that because I was already under time stress when I got there. So the idea is that what biologists do then is that they say, actually, because we have different sites, and these different sites may evolve at different speeds, different lambdas, if you will. It doesn't make sense to fix these probabilities p the same way for each site. So they then decouple the problem by saying we solve one of these problems for each site and then multiply it back together. And that makes effectively m equal to 1. Of course, then it's
much easier.
Yes, absolutely. Except that it's not exactly correct, because because you would still want the length of the times that you get to be consistent, and so it would only be correct if you allowed lambda to change on each edge.
But in your experiments, you also did that. You just
yes,
the
exactly. Yes, yeah, of course, yes. Yeah.
Another question? Yes.
So distances on a rooted tree, I think, form a special kind of metric called an ultrametric, something like that.
Right.
Has anybody ever used methods from the theory of metric embeddings?
Yes, in fact, there's a whole other class of methods, which I don't know well. These distance-based methods. There's a huge literature on this. In fact, I think biologists will use a range of different methods, and they want to see confirmation of at least the topology across different methods.
These are actually Steiner trees. So you're where the branching occurs,
right?
And you don't know in advance. Those aren't prescribed nodes, right? So.
Well, right. In the big ML problem, you don't have prescribed nodes,
right.
But in the small ML problem, you assume that you have, you know the topology. Then you know the nodes, but you don't know the lengths of.
But the big problem is actually the Steiner.
Right.
Okay.